Everyone, my name is Hao Wen. Today my topic is dive into neurotransfer. Before we are getting started, let me split our topic into four sections. The first part is why are we going to use neurotransfer, and the second part is how do we move from style transfer to high quality style transfer. And we're going to explore some new approaches in the third section, and finally hopefully our result can deliver a solid conclusion on how new approaches will improve the resolution of the style transfer. And before we're getting started, let's think about a question. Can anyone be an artist? The question, if you're a person who come from 2014, the answer will be no. But today, the answer is yes. Because at that time, old-fashioned Photoshop filters can only take static photos, and they can only tweak the picture a little bit, and those features are highly handcrafted and limited. And you can see down below here, people took photo for sunset, and they twinkle it a little bit, and they will come to a static hallucinate at night. And the breakthrough comes from Gates' work, neural style transfer. It simply makes styles from multiple images by taking a weighted averaging of grand matrix. What is a grand matrix? We will talk about it later in the project. And before we're going to dive deeper, let's talk about VGG first. So what is VGG? VGG is proposed by Visual Geometry Group from University of Oxford, and they came up this idea when they're going to apply it to a image classification competition. And in 2014, they won this competition and beat all other teams with their unique convolutional neural network design. So let's look into how VGG16 is successful, because it can generate feature maps and extract features during layer by layers convolution filters. And as you can see here, the first picture is an original cat picture, and when it feed into the network, and you simply take a slice of the convolutional neural network, and it works because it can filter out the low layer feature map. And in the second picture, you can see the feature map mainly focus on the whole picture, on the whole big picture, and it can analyze the boundaries of the cat very well. And the second high layer feature map, it mainly focus on the textures of this picture. Image representation help in style transfer. Well, this nature of encoding representation itself is the key to style transfer, because it can be used to calculate loss between the generated image with respect to content and style image, as training the model over 10,000 times per class, and the model is able to generate similar feature representation for many different images, given they belong to the same class or similar content or style. And it makes sense because they use different in the value or feature representation. And this guide us to use a VGG to generate to combine with style transfer. The important thing is, how do we make sure the content image and generated image are similar with respect to their content and not style? That is the problem we need to solve. And similarly, how do we preserve the content from the image from the style, because style may have bigger effect on the resulted image. At the structure of VGG16, and assuming that training these 64 feature maps, they might have learned a few patterns of the cat, such that some neural units can be activated when they see a straight line which might come from the cat, which might not make any sense to a human eye, but has huge value to this model. This detection of straight lines or some other pattern is called learning a feature representation. And consider the tense convolution layer of VGG16, which uses a 3x3 kernel with 512 feature maps to train and finally generate a output of 28 by 28 by 512 image representation, which is 3D representation just for simplicity. This certain units can generate representation help in style transfer. This nature of encoding representation itself is the key to style transfer, since it used to calculate loss between the generated image with respect to content and style image. As training the model over 10,000 of image per class, the model is able to generate similar feature representation for many different images, given they belong to same class or having similar content or style. Hence, it makes sense to use the difference in value of feature representation of the generated image. And think of the content image C and generated image G are similar with respect to their content, but not style. While on the other hand, how do we make sure that the generated image only inherited the similar style representation from style image and not from the entire style image itself? Gated do is separate them and use some conv layer as the content loss, and some part of them are utilized to form a style loss. There's only one single model being used in this in the picture before. And why does style loss actually works? The equation of finding style loss is quite simple. When you look at the feature volume in a conv layer, it can be separated into 256 channels in total, and you smash it like a piece of unrolled vectors, and you get a long vectors that contains all the features. These are numbers. The array, there are 256 channels of size 52 by 52. Now let's assume there is a channel A whose activation units may get activated when they come across an image section containing black and brown strips. And then there is a channel B whose activation units may get activated when they come across something similar to an eyeball of a cat. So if both of the channels activate together to the same input, that's highly possible that image might contain a face of a cat, because it had two channels with high values, and that's what we called gray matrix. And we use this gray matrix to measure the degree of correlation between channels, and this acts as a measure of the style itself. Gray matrix prove that styles are spatially irrelevant, and they have low-level feature volume, mid-level feature volume, and high-level feature volume. They're all correlated, but the matrix could be changed if your input is changed. Deeper look at the convolution layer. When it's unrolled, each roll represents the activation of a filter. In style loss, we use multiple activation layers. That's the scenario lead us to possibility to assigning different weightages to each loss providing by different layers. Loss is quite simple because you just measure the content image and the difference between content image and the generated image pixel to pixels, and thus the loss is formed. VGG is quite big. The size of it is about 426 megabytes in total, and so we need to pick some certain layer for for constructing style loss, and some of them are going to be constructing the content loss. So here you can see in the table we pick 0, 5, 10, and 19, 28 to build the style loss, and the content volume we choose is 25. We look back to what Gatus do. Their result is not that good because they didn't focus on the quality of the image, and if we add the total variation loss into use, then the resolution of our resulted image will be better, and the final loss, which is the synthesis loss, can be generated by these three loss with alpha, beta, and gamma be the hyperparameters. I apply the TV loss. You can see here the case 1 is what Gatus do. Their result contains a lot of noises, and what TV loss is quite simple. It denoise the image and help training faster. It shows the framework of the TV loss is added. TV loss with add-on optimizer, you can see it converges very quickly within 100 epochs. Tested with different gradient descent method, it seems that the add-on shows the best case with only 500 epochs to converge, and using different VGG networks like VGG 16 or VGG 19, we can extract those net to form a smaller net, which increase the training time and win a speed up over 1.3 times more than the VGG6. We get the better resolution result for the network. For listening, the code that I gave to the link will be runnable, and you can test it on your configuration.